No, no. All right.
All right.
Thank you.
All right. So yeah. So say a little about yourself.
All righty. Sweet. Well, thank you, Ted. Thank you, everybody, for being here. My name is Zachary Gillette. I'm the founder of Customs Edge here. And so we build HTS customs classifications. That stands for Harmonized Tariff Schedule. So any company that's importing or exporting has to classify the products that they're sending. And so we use machine learning and a large language model to solve this. So it's a 10-digit code and it does have a structure here. You can see we've got a chapter, heading, subheading, and the US line. And the chapters are broken down into something like electrical machinery or, plastic components, things like that. And we go down the line and get a little more specific. And that US line is the one that the customs departments care about the most because that determines your duty rate. So why did I choose to do this with machine learning? Well, I've been informed that it may not be necessary, but we did it that way anyways. So we got 18,000 records or 18,000 codes is how we have to find just one for one product. And so that felt like something we could pull off with some basic machine learning stuff. Now, online, there's not a whole lot of training data that's readily available. It's kind of spread out. And the stuff that I did find is from Customs Borders Protection, and it's a bunch of legal text rulings. And so that doesn't work very well when we expect a bunch of product descriptions to then go classify our codes. So, in the manual sense of this, humans would get these GRI, general rules of interpretation, and those are maintained by the agency that has all these codes. And so experts, customs brokers, shipping forwarders, all these guys would go off of GRIs to determine, okay, you know, if this product is made of plastic, but it's made for, baby bottle warmers, well, then it's a baby accessory, right? So they do that kind of logic. But anyways, that would take obviously quite a bit of time and require some industry expertise depending on your vertical. So Customs Edge intends to take that process down by 95% or so. So what we did is we took the 100,000 public rulings from the Customs Border Protection website and just focused on a few chapters, scraped them, came out with about 5,000 records. But all of these had legal texts like you'll see here, where it doesn't exactly describe a product in the traditional sense. So using an LLM and a few shot, we transform this into a clean Sony PlayStation wireless stereo headset so that you have a nice set of training data with the HTS code. And after all that, we get like 3,400 records from my little scraping job, just enough to run a small model and train something up. So now let's talk a little bit about what I know the least about. And this is the feature engineering. And we've got Expert, which I believe is just kind of semantic embeddings, turns it into a bunch of numbers that we can compare relatively simple. And then we've got material keywords, product type keywords, attribute, and then brand, and then numerical values like price, dimensions, weight, country of origin. And all of this comes together to hopefully get some decent performance where we are accurately classifying within our chapter subset, because that's the live production vertical focus. We get these HTS codes out of just a product description and an enriched record of all those extra details like brand and weight. So we talked a little earlier about the structure of that number. And so following that same logic, I just split it into 4 models so that we could get down and constrain it along the way. So we start at the top with a chapter. We predict the most likely chapter. Then we dive in and predict the heading, subheading, and finally the US line. But you'll notice that US line has all of the classes in there. And that's because it's a little more general, like it's not constrained by that subheading. Um, so next, you guys want to know the actual numbers. So for the chapter accuracy on the top one, we got a 95, top three, 99. So in the top three, we always had it pretty much. But then as we go down the line, we get to that 70 at that US because we had 18,000 classes, a little better at the heading and subheading. But overall, that's clearly not enough to bring a product to market. So here's where we use the language model to attempt to mitigate some of our errors. But the nice thing about that structure is as we lose probability along the way, we can flag it and say, all right, let's pick it up with the language model and run tandem. But so from there, the language model picks up those flagged edge cases, runs off of those GRIs as general rules of interpretation, and attempts to provide logic as to why it's going to go with a certain classification. And it'll explain that and drop it in the final Excel. So, those two components, that's the layer 4 and 5, the ML and LLM, but we also have basic format validation and then a database lookup if the client has existing assets. And then the US ITC, which is the maintainer of these codes, does have an API to verify. However, it only verifies that the code is a real code, right? Not necessarily you classified it, right? So I talked a little bit about this, but obviously it's the classic story of garbage in, garbage out. If you don't clean up your stuff to have good records going in for predictions, where they match your data set for training as best as possible, you're not going to get good results. So to do that, we enrich any, truncated product names or descriptions or what have you, by going on B&H Photo with a little scraper. They don't have an API. And then Best Buy does have an API. We do web search. All of this is just to get, country of origin, price, dimensions, product description, get that clean. That way we get a solid classification. So, as of right now, we've got a working demo and it can process real manifests. I've got a contact at the UFC who is where this whole problem started from. And so we've run that real data and it does work, which is nice. The tech stack is trivial. We're using Claude Code, Claude as the main model for the language model, and XGBoost for the machine learning. The country stuff is trivial. It's really just field mappings, a little formatting sometimes. And the interesting part that I like here is the OCR intake and a little LLM funnel, just so you can throw chicken scratch in there and come out with some nice records, because we all know how these data streams come in sometimes. And then lastly, the US ITC has all of these codes in a database, so we've got that just to search. So I mean, like I said, I had some opinions that this doesn't have to be done by ML. I'm more than interested in figuring out many ways to do this. I'm sure some of you could figure out a solution better than I. So right now, we're hoping to get this pilot running Q2, and we'll expand into more asset management. But my focus is, we could get into hardware distribution, NFC tags for assets, but I don't want to do that. I want to stick software and integrate. So that's kind of where my head's at. But I'm currently in the process of looking for a technical co-founder or collaborators, if anyone's interested. That pretty much wraps up my talk. I can show you guys the quick video on my website if you want to see. Okay, sure. So the UFC is the fighting league, Ultimate Fighting League or championship. I don't know. I don't know that much. Yeah, they'd be my pilot first customer. Yeah.
Yeah, I'm really curious. What does UFC, how would they use your classification
Sure.
system? I mean,
So
what product are they trying to buy a headset?
Well, here's what they do, right? So they have about 15 international events annually. And for every one of those events, they've got a warehouse over in Vegas filled with, $1 million worth of camera equipment, rigging, all kinds of cables. And those have all got to get loaded on a truck to make it to Dubai by X date in March. And so to do that, they have to have individuals in the warehouse run around, grab these things, inventory, pack it into cases, and then load it up into a manifest for customs to take that on. And customs will reject that if you don't have it classified or if you don't have it in the right format. And so that process alone is, a 300-hour annual time sink for at least one resource. And it gets spread out pretty rapidly as you go saying, where's that cable, please?
This model that you're building, are you trying to replace the customs brokers?
A good question. Yeah, no. The goal here is to complement, because it's funny, even the customs brokers, their primary value add to their customers is getting it on a truck, getting it on a ship, finding the best route, getting it there on time, right?
Mhm.
The minutia of getting the HTS classification, they may guarantee it, but they oftentimes throw it back on the client, the UFC in this case, and they say, can you classify it? Because it's your asset. And generally speaking, they
Been
get
there,
it.
done that in past life.
Yeah, yeah. Yeah. So yeah, very good question. Yeah.
Thank you.
Yeah. But here, I can show you the demo. I just pull up Chrome here. Is that okay?
Yeah.
New window? I got you. No worries. That's me too. So this is our website. And you can see here, we're just going to drag in some sample data. It's a little, blank. We've got some truncated names. And then right now, we're just going to give it a title. And then it's going to go through and do that enrichment process, going through those APIs, B&H, Best Buy, web search. It's going to get product descriptions, weight, price, all of that. And then it's going to do the ML models and classify for HTS codes. It's going to grab those flags with the language model, do the GRIs, and you should come out with a commercial invoice ready for shipping. And the other thing I didn't mention is these ATA carnets. Just like people have passports, items can have passports. And so you don't have to pay the whole tariff duty if your item is only staying for a little bit. But ATA carnets require a little more document management. So that's what this system could do. But that's it, guys. I really appreciate your time.
One more question.
Yeah, please.
Would it be, I don't know, practical or even conceivable? Could you, if you trained a vision model to just look at a piece of equipment, would it have enough information to do a correct classification, or do you really need
I think
the
a
spreadsheet?
vision model at the start of a pipeline would be useful. One feature set was to give the warehouse guys, a camera upload, and they could snap a picture of a asset and a serial number. And in theory, we could log that as a record in the inventory. But what I would say is, because of the nature of these industrial broadcast equipment, they're not easily identifiable with most computer vision models. You might get some random piece of AV equipment, but it might not be that product, right? So at the front of the pipeline, I think it makes a lot of sense. Any other questions?
Thanks, Zach. I love how we know some of these models and like the building blocks, but when you intersect it with a real world business problem with some domain knowledge, then you get this like rich problem like you described here.
Sorry, go ahead.
No, I was just going to ask if there are any last questions for Zach before we move to the next talk.
All righty. Well,
Awesome.
thank you.
Thanks, Zach. All right, we're going to have Armin for our next presentation. Armin is home on his desktop machine, so he has a little more horsepower to do this demo. So I'm going to stop sharing locally. Sorry, grab Zach and connect with him. And Armin, if you want to try sharing your screen, I can turn things over to you. Nice.
Hi. Can you
All
guys
right.
all hear me?
Yeah. So say hi to folks, introduce yourself a little bit, and then go for it, man.
Yeah, okay. Hi everyone, I'm Arman. I'm a machine learning researcher at Rockstar Games, and I'm doing a presentation about some of the work I did at my previous job at Valve, which was about using machine learning to generate procedural animation. And the essential topic here is using machine learning to do pose-to-pose prediction. And I'm going to first start, and just to preface, this is going to be really high level. I haven't prepared any slides. It's going to be an interactive demo where I'm just going to go over the problem that was solved and a high level of how it was implemented. So the thing I'm going to show off here is if you see these two people left and right, the left is essentially ground truth of what the animation should look like. And on the right, we have a machine learning algorithm predicting some of the poses of the animation. And ideally, it should look realistic and close to the one on the left. So let's run that. And you'll see it looks pretty good. I'm just gonna focus on the mesh here. Yeah, and it looks realistic and fine. It is going a little bit fast here. And so what's happening here? And again, pose to pose prediction is all that's happening here. If you look here, you can see these individual poses that make up the skeleton of this character that's being animated. And on top of that, you have the mesh, which is linearly skinned to these poses, which are these orientations here. And all that's happening is given, say, a subset of these bones, like say the core skeleton, we're predicting the remaining helper bones to help mesh deformation look realistic. If I zoom in here, you might see this one right here is maybe a core joint in the skeleton. So is this elbow, and so is maybe this shoulder point right here. And the idea is given these three as an input, for example, or maybe the entire skeleton if you wanted to, some subset of the core skeleton, we're going to be predicting, for example, these four helper joints here. I'm just going to kind of circle them with my mouse a little bit. We're going to be predicting these ones here. So this is our output, and our input is, for example, some of these core joints here. And I'm just going to circle some that look like they're nearby. Yeah, so that is essentially the work, the problem that was solved. And the question is like, how do you go about solving this? And it's a pretty simple problem statement. And I'm gonna showcase, oops, misclicked again. There we go. An interactive application that I had made to kind of prototype the ML algorithms for this. And if anyone's familiar with radial basis neural networks, that's essentially the core algorithm that was used. You can also use just traditional neural networks. That's also something I experimented with. But radial basis neural networks have some nice properties. So just to highlight what's happening here, imagine on the left you have an input pose, and on the right you have an output pose. So this blue input pose corresponds to this output pose, and this red one corresponds to this red output. And as you would imagine, if I interpolate between the inputs, I should interpolate between the outputs. Right now, the input is only looking at translation, but you can also do rotation if you want. And it's still, the interpolation on the output looks similar and the same. The big thing about why we don't necessarily want to use splines for the output is because we want to have an arbitrary input. and I will make that a little bit more pronounced here. Now it's not obvious how you would interpolate. You can't really interpolate in a permutation invariant way with splines for the output, but you can here. And yeah, you get some interpolations, and I'll just highlight real quick that this interpolation does not look like it's taking the shortest path. And another problem with predicting rotations is that rotation representations may not be smooth in the right way if you don't use a good representation. But if you do use a good rotation representation, you will get that smoothness. And I will do one last showcase with the splines, so you can kind of these input splines help things look a little bit nicer. So you can see this interpolation looks reasonable. But if I switch back to just predicting a naive rotation representation, you get this bad artifact here. Sounded like there was a question.
Nope, not
Okay.
yet. Keep going.
Okay, I think something else pinged on me. Okay. Moving on. So here we have one input to one output. Now, if we want to do one input to many outputs, you can have that set up as well. And you can kind of see these interpolations look reasonable. And lastly, I will showcase many to many. Now there's a lot of craziness going on the input poses, but if the model performs as we expect, we should expect something smooth on the output, and we do see something pretty smooth. And just to showcase that you can go outside the spline, let's try and move these closer to the purple. You'll see the output kind of get closer to purple as we make these adjustments, including adjustments to the rotation. Try and line those up a little bit. And yeah, we didn't quite get there, but they're not exactly the same on the input, but there you go. Now it's not the same. And yeah, so you have a simple solver here that takes in 60 poses. That's 3 parameters for translation and 3 parameters for the rotation. And outputs 60 pose, which is the very same, and you get the smooth interpolation. And I'd say that if I were to go more in depth in this, which I may in the future, the topics I kind of cover on is like comparing radial basis neural networks to traditional neural networks, because I think there's a lot of intuition to gain from comparing the two in ideas like metric learning, and also diving into rotation representations, because that is also a really interesting topic in machine learning, and applicable not just to animation but robotics, because robots are also using these 60 poses. And yeah, I will do one last showcase of the animation, hopefully bring it all together. Yeah, again, you have some subset of input poses on the skeleton, and they just predict the remaining ones. If I were to turn off the solver, you'll see that this does not necessarily look as great. Let's find a frame where it's kind of really bad. So here the joints are just not being predicted at all, which is obviously going to look bad, but yeah, looks good otherwise. Yeah, that's kind of it. Let me know if there's any questions.
Right. Questions for Aman?
Yeah, thanks for the talk, first of all. Just a question around the motivation behind this project. So is it more to are spines computationally too expensive, and you want to do this with ML prediction to make it faster or more reliable, or what kind of is the reason behind?
Yeah, good question. I should have covered that. Yeah, so the motivation here is essentially this animation is 3,600 frames, and there is a lot of these helper joints. And again, they're just there to help mesh deformation look realistic. Like, for example, you might have one that at the bicep to allow for biceps flexing, for example, and you might have a bunch to make it look realistic. And it's not obvious here, but an overwhelming majority of the bones here are these helper joints to help mesh deformations look good. An artist or an animator may not want to author all these poses across all these frames. So instead, what they can do is just give a couple of data points of where those joints or poses should be, given a small subset of the skeleton. So give a couple of samples, like if I have like a bicep I want to flex, maybe here the bicep joint, this helper bicep joint is here. When I move my arm like this, it should be up here. And then I use this essentially interpolation algorithm to interpolate the rest of the poses. You don't need a neural network to do something as simple as this, but if you want something more complex, you'll need a neural network to kind of to match a more complex distribution. And that's essentially the motivation. Animators and artists don't have to author all these helper joints. They can give a couple of data points and then procedurally generate them in the runtime dynamically. And if you can make them fast enough or efficient enough, it's totally worth it.
Great. Any other questions? All right. Awesome. Thanks, Armand. And I think I will be taking you up on digging a little deeper into these radial basis networks and some of this other fun stuff with representing angles and stuff.
Yeah. Thanks a lot.
All right. So next up is Tony. Do you need a computer? Do you need anything? Okay.
All right, good afternoon, everyone. I'm going to get calibrated to the microphone here. This is kind of a huge crowd for this event, so appreciate everyone coming out here and hope to make it a good use of your time. The subject of my talk is going to be about the DeepSeek OCR model or models. And in putting this together, there's a few different layers we could maybe talk at today. And I would maybe like to get a show of hands to see what would be most interesting to you. So like we can talk a little bit at like the mechanics layer of the models themselves and the training and the components and like the real detail layer. We can talk at kind of the application layer of like, how would you use this in real life or kind of how we're using it. And then we can get kind of out into speculation of like the research DeepSeek is doing and why they're doing it and kind of directions that might go in the future. So I guess what would be interesting to you? So raise your hand first if you would like to focus on like the real in the weeds training and model components. Okay, that's about half. That's about half. Okay, impressive. Application layer, the other half. Okay, okay. And then people who want to speculate on DeepSeek. We got a couple. Okay. So I'll try to adjust accordingly here. If I can figure out how to increment the slides. maybe I'll just click. Maybe I won't just click. I'm pushing the arrow buttons. Oh, there we go. There we go. I tried right, left, and up, and I had to push down. So very good. Okay. Well, pleasure seeing you all on a Saturday. My name is Tony Sclafani, and I'm here representing a business that I founded called Integral Business Intelligence. And really, we exist as a business to provide the system integration between apps and software and programs like what Zach talked about. I've never met Zach before, but hopefully we talk in the future. Between kind of all of the new technology that's coming out and the existing business systems that people already have in their offices. So I live in Otay Ranch, kind of down near the border relative to here. So when Zach was talking about customs and shipping, like that's a lot of what I see on the 805. And so you're going to have these businesses that are going to want to use Customs Edge, let's say, but they're maybe going to say, well, I know nothing about AI. Here's kind of the systems I have. How do I integrate it? That's the role we want to fill. So across markets. My ideal customers are small and medium businesses with sensitive data. And sensitive data can mean really a lot of things, not necessarily HIPAA, not necessarily legal, just anything people don't want to put into a cloud API with a hyperscaler. And so in the course of doing this type of work, we do a lot of like typical ETL type of operations to get things into a database for like retrieval augmented generation, things along those lines. So we're extracting the data from the documents, we're transforming it into however we want to store it, and then we load it into, whether it's a relational database, vector database, knowledge graph, kind of whatever the right tool is for the job. And so there's a big focus on going like full end to end from the paper documents to digital, and then from digital into the database. And when we look at a document, really we're interested not just in the text, we're also interested in the structure of the document, like the headings, the chapters, the subsections. And I'm, I don't know, maybe overly interested in like tables and charts and images, because we put these together to encode like a lot of meaning. And if we're just extracting the text, we're missing a lot of that information that comes with it. So I'm always looking at like, how can we get the most out of the existing documents? And so there's this really cute illustration by the IBM Dockling team. And this kind of shows on the left, you have some regular business graph. This is a stacked line graph. And then on the right, they're showing you that from this visual information, they have extracted numeric data and made a table. So just to kind of show the concept of what are we trying to do here. Okay. For people who are also interested in this type of technology and would like to walk away from this event with things that you can use, here are a few of my favorite tools. The first is called Marker by this company, Data Lab. And they're interestingly the #1 citation in the DeepSeek OCR papers. So like they're someone to follow closely. Then you have the Dockling team at IBM. And then there's a program out of, I forget if it's Belgium or Berlin. It's a European city with a B. It's called Kreuzberg. And Dockling and Kreuzberg are similar, where they're sort of software packages that bundle up multiple extraction pipelines into one thing. So it's like one app that you can put in many different types of documents and get your digitally encoded data. So like Kreuzberg is an example, connecting again with Zach for OCR uses Tesseract. So Kreuzberg does a lot of stuff. It's on top of Tesseract, et cetera. And then another one I'm going to point out here is DeepSeek OCR, and we'll talk about why that one is unique and interesting. So one of the limitations that I had kind of mentioned is, how do you get this table and chart data out of documents, and particularly like images? Like as an example there, if we think of like US patent filings, there might be a lot of images, and you might have pages that are images only. So how can we go through some ingestion process and get that data, or get as much of that meaning as we can, so that we can use it in downstream applications? And until now, it seems like a lot of the focus on the visual model side is on like really small vision models. So the IBM Dockling package comes with this, or designed to work with this small VLM. It's a 256 million parameter vision model. And the challenge that I've seen is that, like, when the models are this small, they don't encode a lot of intelligence. So they see an image, but they can't give you sort of the level of explanation that you would get from a human. So there's this problem. The vision side has been small models. The thing that I find interesting about DeepSeek OCR and how it's kind of overcome that limitation, and this is a little bit different than what I think Ryan was pointing out a week or two ago, is that it comes coupled with a much bigger decoder. So DeepSeek OCR comes with this 3 billion parameter vision decoder. And so that's really interesting. It's like, okay, if we've been limited by these couple 100 million parameter models, what can a 3 billion parameter model give us? Okay. And so when I had first talked to Ted about doing some version of this conversation, that was right around the time DeepSeek OCR was released. Probably early November is when we talked. So it came out on October 21st, and we've sort of had this talk kind of on the shelf for, I guess, a few months now. And then surprise, surprise, like a week ago, DeepSeek OCR version 2 came out, right? So this is interesting because now we can compare what we were thinking about a few months ago with what came out a week ago, and where we think things may be going a little bit. Worth pointing out here, I'm going to use my laser pointer because I rarely get to use it, and my kids run around the house with it and they have so much fun. So I might as well have fun with it too. I think it's really worth, I'm sorry, I'm struggling with this microphone a little bit. A little farther. Am I speaking through the microphone if I hold it here? All right, I'll try my best. Okay, so it's worth pointing out the research purpose of these two papers and models. DeepSeek, I feel, makes it very clear that this is research in support of a broader mission and endeavor. I mean, you all know this, they're not in business to become the best OCR model. OCR is like a platform for them developing new techniques for things, which we can talk about. The first model that came out, they're really focused on compression. We'll talk in a little bit more detail about what that means. And what I didn't expect is in the new model, they're really focused on reading order. So how do humans read the document or go through a document versus how does an LLM go through a document? Kind of a unique twist on this. Okay, so the first paper that came out, this is the one from around November 1st. They say the work represents an initial exploration into vision text compression. How many vision tokens are required to decode N text tokens? So like if I have a piece of paper with however many tokens on it in text, that's a thing. If I take a picture of that and if I compress that, how much compression can I do and run it through the encoder decoder and get the right answer? So this is like a very empirical type of a paper. This is the architecture of the model. And I will probably iterate quite a bit here. And it's very, again, worth pointing out, all of their attention is on this big box. They call this whole big box deep encoder. And we'll come back and talk about that. And then you have the 3 billion parameter model that I had mentioned. This is they call it the decoder. And so those are sort of the two different sides of this. And they're also trained in two different steps. They train the deep encoder package by itself, and then they come back and train the full package, including the decoder. And we'll talk about that as well. So starting with the decoder, the way this should be working is a user provides a prompt, and it's going to get some information coming in from the images, and it's going to give you an output. And so, like, as you would see here, this is just like a 3 billion parameter model. It starts out not being anything special really with regard to vision. So the way they're training it or constructing the pipeline, so the encoder side, sort of like a 3 billion parameter kind of standard-ish language model. On the encoder side, they've got 3 different, I guess you could call it models, kind of put together in a pipeline. So this is actually like a bundle of models, and you'll see that again in DeepSeek OCR 2. The first one is the SAM model. So here we're submitting an image of a piece of paper, and the SAM model is determining, like, is there a thing that I care about here? This is using local attention. And if we use like a 16 by 16 pixel size, it starts out with this 4,096 tokens. So you take the image, you're converting it to embeddings, and you've got 4,000, 4,100-ish, let's call it image tokens. And like the whole point of the paper comes down to this next step, this 16x convolutional compressor. Like, this was the whole thing. This is where they did something different to see what they can get away with, kind of, or what can be done in terms of efficiency. And so it's like this hard-coded reduction in size, 16x, to reduce, think of it as like the size of the embeddings here. And we'll go into a little bit more detail shortly. So we take an image over on this side, we go through the SAM model and produce embeddings, we compress the embeddings, and then we send it to the clip model to say, like, okay, what does this mean? And the clip model is using global attention. And so that's kind of why they want to compress things so much, is to save on computation. So in the SAM model, we talked about how we have these 4,000 vision tokens. They get compressed in that 16x compressor down to 256. So fine, what are we talking about? We're saying we're taking some information, we're compressing it into tokens. The question's like, okay, are those output tokens any good? Like, you can compress data. Is it useful? Is it any good when it comes out of this thing? Et cetera. So that's like an open question. And then the thing to keep in mind with the compressor is that you can control the resolution. So like, if you're compressing the images and getting bad data, you can go at a higher resolution and maybe get a good result. So you can kind of adjust the resolution to deal with quality. And so here's kind of the way their results played out. They tested with different numbers of tokens, like text. Like, this was the image on a page, or sorry, the text on a page. So between 500 and 1,500 tokens. And they said, well, if we compress it down to 64 tokens, or if we use 64 tokens, we have these results. 100 tokens, we have these results. And again, different compression ratios. So if you can compress it 10 times, you have 97% precision, they call it. So in other words, you can compress the image of the page 10 times and get really close to the accuracy of all the text that's on the page. It's kind of dense here. Okay. So how do they do that? So this is the 2-stage training pipeline here. So first, they train deep encoder on its own here, where the SAM model gets trained. The compressor is 2 layers of a convolutional neural network that gets trained. The clip model gets trained. They leave out that 3 billion parameter decoder. So this is all getting trained to produce the embedding representation of the image. And then they go back in stage 2 and they add the decoder model. They freeze the SAM model, they freeze the compressor, they retrain or continue training the clip model alongside the 3 billion parameter decoder. So like my understanding is this 3 billion parameter model is coupled with the deep encoder, they call it. So like that 3 billion parameter model becomes really good at understanding the embeddings that come out of deep encoder. And so, as I mentioned, their finding is they can do like a 10x compression ratio with really good accuracy. And then when they try to go up from there, it starts dropping off quite a bit. Question.
What do these like vision tokens kind of look like? And like, are they using like the convolutional network to just like be like, okay, give us like a smaller token representation of the incoming token representation, or like how are they getting the compression?
Yeah, so from my understanding of it, the vision token, I'm going to think of a way, I'm going to do my best to answer your question directly. And if I can't, might be in my notes here. But the vision token, let me go back to, I guess, this image. The vision token is like, it's just a embedding vector like anything else. It's not like a different type of a token, right? Where this decoder model, my pointer turned off again, this decoder model is able to accept, through like a text tokenizer, it's used to a certain embedding vector, right? And the output of deep encoder is trained to be the same type of a vector. It looks like, do you have Ryan, were you going to add on here or jump in?
I can maybe help a little bit.
I would appreciate it.
Yeah. So what's happening here is you have an image, let's say it's 1024 by 1024, and then it's split into little tiles, little patches of 16 by 16. And then at that point, it gets turned into some vector, some embed. So you lose your 16 by 16. And then at that point, it's just a list of numbers saying, like, I think this is what this looked like. And then it goes through SAM. And what SAM is doing is it's looking at that vector and it's looking at the ones that are next to it and trying to interact those a little bit. And then at the end, it's giving you some like transformed token, but it's just some numbers. And you hope that that's speaking the same language as your clip and your decoder and everything else after. But the input is originally just like take some numbers, transform them, and then after that it goes through all of SAM, and SAM's a whole bunch of convolutions and everything. So that's the like conversion between those steps.
Yeah, the one high level comment I have is that if you were just using a VIT like classifier model and you're grabbing the bottleneck, then your vision embeddings at that point correspond, I don't know what's the right word, geographically to the original page. So you have like a vision token that says, what did I see in the upper left corner? What did I see in the region next to that? What did I see at the top center? What did I see at the upper right corner? So on and so forth. Okay. When you talk about segment anything, okay, that was designed to find objects on the page. And so now you're no longer restricted to just geographically, that's not the right word, apologies, but geographic tokens. So that if, for example, I don't know, you got a fax and the bottom half of the page was blank, all right, you would just be wasting half of your tokens in a regular VIT saying, I see all blank, I see all blank, I see all blank, all right? Segment anything is going to say, this is where I see objects on the page. And so you're now not sort of in, Cartesian geographic coordinate space, you're now in like object space. Obviously, the objects still have information about what do they look like and where are they on the page, but it's not strictly one for the upper left corner, one for the lower right corner, and so on and so forth. And then that's the information that with the convolutions that we want to actually compress.
Thank you, Ryan. Go ahead. Go ahead.
Yeah, one last piece. So you can see like from the slides there, you start with 1024 image, and then it gets split into these little tiles. And when you do that, splitting into 16 pixel by 16 pixel, it becomes 64 by 64. So that's that huge.
There are 64 tiles. Yes.
It's
So
64
64
height and
tiles high and 64 tiles long. Yes.
So
Yes.
that's a very high number. If you pass that to a language model decoder, then it's slow. And so this 16x, what it's doing is it's actually just 2 layers of convolutions. That's just reducing height 2x, reducing width 2x, and doing that twice. And so that's how you go from the 4096. It's literally just 2 layers, just going reduce this, and merging those together.
Yeah, that's exactly correct. And I just want to emphasize a couple of things that Ted and Ryan, you just said. So thank you very much. To Ryan's point, you're taking a 1024 by 1024 image. You're saying, I'm going to make tiles 16 pixels a piece. You end up with 4,096. That was the original number of vision tokens, right? And because the clip model has global attention, doing that 4,096 times is a certain cost, right? And so they were saying, if we just build this compressor, I mean, I just think of this as a funnel, and it's taking all 4,096 tokens, smashing them down to be 256. What's coming out of that? 4,000 going in, 256 coming out, and it reduces the computation on the back end. What comes out of clip is just, as Ryan said, another transform vector. And through that sort of 2-stage training process, that decoder learns to understand that this thing means that thing. So does that answer generally? Okay.
Just like the vision transformers, if one uses the mean and standard deviation concept of tuning that, perhaps would that speed up, because it looks like the DeepSeek is definitely concerned about performance or something like that. I don't know if they have fitted that into this, like the concept of vision transformers, or like the noising, denoising of the, what's that model? I forget the name. Anyway, that's another way of doing that. So I was just wondering, randomly I was thinking, is the DeepSeek interested in embedding that into the process?
Yeah, I could not comment other than to say it's not mentioned in the paper. They mention a couple things that they've tried in both different papers and like some things that have failed, but they didn't mention those aspects.
The reason why I brought that, the noising and denoising, that, that's, what is that? Totally spaced out. But anyway, those are all various different techniques for processing images and getting the accuracy, fairly good accuracy. And because it looks like they are using multiple models, that's why I brought it in. I asked.
Yeah, you're absolutely right. And I mean, when these models like DeepSeek OCR are announced, you think it's one thing, but then you look into the paper and it's actually a pipeline. You'll see that even more in the next model here. I see. So in terms of applications, DeepSeek points out that you can use this for OCR. They point out you can use this for LLM, VLM pre-training, which I think is like a major flag towards what are they thinking about doing with this stuff. And then part of the paper that really is of germane interest to me in the beginning of kind of my presentation here is this concept of deep parsing, they call it, where, and I've sort of smashed some images together. So in the paper, they show, okay, they've taken this page on the far left about macro news and views. And this is like your typical business document. It's got some text, it's got some charts, etc. And by running it through their model, you can get document layout, which is the second image. And then the third image is the sort of content rendered as Markdown. And then the fourth image is you can actually get the data out of the document. So now we have like one tool where we can put in a document and get a lot more information out of it. Great. However, if you were to download the model from Hugging Face and just run it, that's not what you would get. So I will share a little bit of secret sauce and like lessons learned and things that we've done that if you want to do this kind of thing might be helpful to you. I will not walk you through this entire flow chart here, other than to say to do the deep parsing, you need to do like a 2-pass operation. The first pass goes through the document and it identifies all of the text, and it will tell you where images and charts and tables and things are located in the document, but it will not extract them. So now you have, 2/3 of the text or 2/3 of whatever is important to you, but you don't have everything. So you need to do another pass through the document, and this requires a different kind of prompt configuration to tell the model what you want it to do to extract the stuff. And then there's an icon at the bottom of a sewing machine, because then you need to stitch it all back together. You need to put your description of the image, where it came from in the document, and your description of a table, where it came from, etc. And you can end up with a output document that contains all of the information. However, now we can think like, well, where would that go wrong? Well, if you have the computer or the model generate a description of an image, it just sees that image on its own. It doesn't necessarily know the rest of the context on the page to know, like, why do I care about that particular image? It might just say, in Zach's case, if you took a photo of some high-end camera equipment with the UFC, it might just say, this is electrical equipment. But we would like it to have more information about the type of camera and such that it is. So what we would propose or do in that scenario is, when we go back, can't even see the laser pointer here. When we go back and do the second pass, when we send the image into the model, we want to send the image with the rest of the text that's on the same page or some nearby text. So the model is told, given this image and given this information about what we think is going on in the image, generate a description. And we find that that gives you much better results. They're not perfect, and there are some, I guess you could call it hallucination type things to watch out for. Like one of our experiences was with patent documents that use chemical symbols, where you can put in the text, but if the text is sparse or doesn't describe maybe what element that you're seeing, it will guess an element, or it will say something that's not in the image itself. So there's some things to be concerned about there. For anyone who wants to be or get a little bit more hands-on with this, we put our Jupyter notebooks for running these models. And like, there is some nuance, like you have to use particularly old PyTorch versions and so on. So we've got some notebooks here where you can do the dual pass processing, so you can get the image descriptions out of it. And then we do have a couple of YouTube videos and a little bit of a performance overview on this and a couple other things. In terms of processing throughput, I remember when Ryan did the OCR presentation, we talked about like computational cost maybe. And like in my world, I feel it's like relatively cheap. We can run this and process something on the order of 1 gigabyte an hour of business documents, which is like a good amount of information at a pretty low cost. And that's through the 3B decoder and like 2pass and all of that kind of stuff. And for like these type of businesses that are trying to do things with information, it's a pretty small, pretty manageable cost when it's like small time batches, maybe not production scale for Google or someone like that. Okay, so that's kind of like the long and gory detail on DeepSeek OCR, the original. And then last week came out the model in the paper for DeepSeek OCR 2. In this one, like I had said, the focus on the first model was compression. The focus of the research for the second model is reading. I call it reading order. They describe it a little bit differently, but it's very interesting. They again focus on deep encoder, and they want it to be able to do causal reasoning so that it can intelligently reorder visual tokens prior to LLM-based content interpretation. What does that mean? They're saying that if you feed text into an LLM, it sees the first word, it sees the second word, it sees the third word, and it just goes through regardless. But when a human looks at a page, like we had this business document before, your eyes might go around in a spiral or some other way, or based on headings or subheadings, you'll view different parts of the page differently. And so this is like an experiment for them to test, are there other ways to do that? And might that change sort of the attention and the focus and the weighting of different text in a document? Okay. Some of the comments, some of the excerpts from the paper, they say that the human visual system functions as visual tokens, locally sharp, yet globally aware. And this is something you'll see them thinking about in the first paper as well. They mentioned that existing encoders rigidly scan tokens from top left to bottom right, which is, Ted, something you were kind of hinting at a little bit earlier. And the authors say that visual tokens should be selectively processed with the ordering contingent on visual semantics rather than spatial coordinates. So again, rather than go top left to right, top to bottom, try to learn what's important on the page. And their objective or goal or such is to reconsider the architecture of these VLMs rather than flattening it, flattening the images. They feel that that creates a bias and it ignores the way people actually read the papers. Okay, so what did they do differently here? This is a much shorter discussion now that you're familiar with the gory details of Deep Encoder 1. So Deep Encoder 2, what they did was they took the clip model, so the right side over here. This thing shines on the floor. Okay, I like the laser, but it's not working. Okay, oh, can we see it on the screen? Much better. And I guess for the 30 people, thank you, that are following on a webcast, that's much better for them too. Okay. Let's see here. Where did we go? Okay. So they've replaced the clip model with this LM as vision encoder. What is this? What are they doing? What does this mean? This means they've deleted clip and they've put in a pretty close to an off-the-shelf LLM. And they've said, instead of clip getting a vision token and generating a word for what it means, can we add another LLM to do it? Okay. DeepSeek OCR, the original paper, had a 2-stage training pipeline. This one has 3-stage. So first, they train this deep encoder. Got the SAM model. You've got the same compressor. They apparently like the compressor that they had in the first paper. And then they train this Quen model, which is very small, 500 million parameter model. That's step one. Step number 2 is where it gets interesting and they do something different. They call it this query enhancement. So inside sort of this green sketch mark, this is like model weights. These are like trainable parameters. I'm trying to decipher if this is actually like some type of content that they're giving it, or if it's like a bolt on to the model itself. But on the left and the non-causal side, that's the image vectors. On the right, the causal side is like text vectors that seem to be, they're being trained to learn or to be taught. They're sort of like I'm trying to think of how I would describe it, as like it's almost like a placeholder value. It just like starts out as numbers that are random, and they get frozen into like whatever the learned representation ends up being at the end of the training run. And the point is that after that second stage of training, the third stage is back to focusing only on the decoder. And at this point, it's getting the output of that intermediate LLM, and that's the new representation of the vision. So it's like in stage 2 that this overall pipeline is learning what's called what I'm calling the reading order here. So what are their findings? It works. It works to replace CLIP with this LLM. Their benchmark score went up like 4 or 5%. And they continue to say this has 2 primary production use cases. One is you could have an online OCR service. And again, this is where we're thinking about what is DeepSeek doing with what they're learning. This can read images, documents, specifically they say for DeepSeek LLMs, and then a pre-training data pipeline for batch PDFs. Okay. So the second paper, obviously we went through that much faster. The point is they're giving it the ability to understand the reading order on the page. And they bake that into this intermediate model so that when a user query goes into that 3 billion parameter decoder, it should be like weighted to be more relevant to like what's on the actual page. So a little bit of research in the first, little bit of research in the second paper, and then we and you hopefully get the benefit from that for doing text extraction and image recognition and so on. So would love to talk more with you all. And, I would love to connect with you all on LinkedIn and talk further this afternoon. Thank you so much.
A quick comment, intuition on this reading order thing. So imagine that you had a page with 2 columns, and just oversimplifying, on the first column, you have paragraph A, B, C, and D. And in the second column, you have paragraph E, F, G, H. Okay. If you do the standard raster order, and I know that like each paragraph might be multiple patches or whatever, but oversimplifying things, then when you feed those tokens into the decoder, you're going to see A, E, B, F, C, G, D, H. Okay. This decoder is the regular DeepSeek 3 billion LLM that they've now fine-tuned a little bit in order to be able to do this OCR task. So it's an auto-regressive LLM. Every token can only look at things that came to its left. So that means when you see A, E, that E can only directly attend to A. Even though reading order wise, logically, it should know about B, C, and D already, but it hasn't seen them because you physically ordered your vision tokens in that order. That's the problem that they're trying to solve. So eventually it mostly gets it right, because by the time you get to H, it can kind of look back and see all of A, B, C, D, E, F, G and kind of piece things together. But every now and then you might get into a bind where you really wish you knew that, and you make a bad decision, you start heading down a wrong completion path. Okay. So just simply by reordering the vision tokens, they have the same XY coordinates. It's not changing the actual, conceptually, it's not changing how many or what vision tokens, but by simply passing in a vertical column of patch tokens and another one, and you say A, B, C, D, E, F, G, H, you're just giving the autoregressive decoder a little bit more of a boost in its ability to understand the text, versus 90 whatever percent of the time it still figures it out, but it does have to do a little extra work to say, oh, A, E, B, whatever, and just kind of decode it. So hopefully that intuition makes sense. Question?
Yeah, I have been building a product that ingests the PDF of an exam for school. And I've ingested exams that have 2 columns, just like you described. OpenAI has solved this problem. I can ingest it and it will correctly pick out question 1, 2, 3, 4 on the first column and 5, 6, 7, 8 on the second column. And give me the questions in the right order. So I'm not sure what you're trying to solve that OpenAI hasn't already solved.
I mean, one comment I'll make is that if you're using like, Chat GPT, you're talking about a model that's like 500 times bigger and slower than DeepSeek OCR. Okay, so it's not exactly a fair apples to apples comparison. And we're not saying that DeepSeek OCR v1 wouldn't ever do the 2 columns right, but there's maybe this 1 or 2% of the time when it isn't able to do question answering and other things quite as good as if you gave it in the more logical order.
Ted, I'd like to add on to that a little bit. You're absolutely right that frontier models are the frontier models for a reason, right? And I'm maybe reporting to you on the state of the union of the non-frontier tools that are available, with the idea being that like our potential customers say, that's great. I don't want you to put my pre-filed patent documents into ChatGPT or a frontier model, et cetera. I would like to do local processing. So it's like my job to understand, what are the tools available for like local private kind of processing, with this being one of them. And to your maybe point is that like reading order itself is not necessarily wildly sophisticated and isn't cracked by other methods. And in the research paper, they use this as like an exploration to get hints at what further research they can do towards like native multimodal, towards native 2D spatial awareness. So like these are sort of feelers in the dark for hints towards future research, rather than like this is the new hottest thing, in my opinion.
So from my understanding of what's going on here, I think that the positioning encoder was essential, because what they noticed on the first model during their compression is when you took those tiles and you took something like a table or something like 2 columns of text, you would end up having, like you said, Ted, a jumbled up mess. And so their solution here was this visual understanding of the context. I don't think it's necessarily like, an end all be all solution, but yeah, I think it makes a lot of sense. It's very cool. Thank you.
Thanks. Yeah, another question?
Well, I do wonder if there was a case where it needed to view a certain part again in order to process it in a different way. Like say there's some information in a certain sentence that's missed, and then it realizes later, or from a certain patch that's missed, and then it realizes later from another patch that there was some information that might be encoded there. Would there be any sort of research into reprocessing something old but in a different way, or in an old patch in a different way?
So, I mean, from what I've seen in the paper, they don't describe this particularly. The way it appears to me that DeepSeek thinks about this is balancing that global view versus the patches. And like in the original DeepSeek OCR model, there's like different modes that you can use in that model. Some of which I think get in that direction, but no, not in the sense like with what we're doing with the reprocessing, the multiple passes through the pipeline. So I guess my answer is I haven't seen it in their official docs. And if you're interested in that kind of thing, I think it's like a DIY approach.
Yeah, in this context, some of the Middle Eastern languages actually go from right to left. The Japanese, I believe, is top to bottom. So it has to recognize this type of orientation and then proceed for any meaningful output.
Yeah, it's a great point. And I know to some extent, these models are multilingual. I don't know what all languages off the top of my head they support. I have no doubt it's going to include Chinese and probably Japanese, but I don't know in terms of other languages, right to left and so on.
I know the version 2 is brand new, but did you try it out and you saw that it's actually better than the previous one, or?
So I actually did not. As soon as I got into the paper where it says they reused the same 3B decoder, like it just, I haven't had the need to go do a taste test yet between the two of them.
Have you had any scenarios where you think the model's deficient, like you're hitting any accuracy problems or?
Yeah, I mean, I still continue, like this is my biggest area of interest is in the like table, chart, graph, image to text. I have not seen anything that I'm blown away with. I feel like this model is like a great step in the right direction. Not anywhere close to human replacement at this point. And like, I welcome much bigger like decoders that can more intelligently explain these things. So I feel this is like, I don't know, 60% happiness vibe level or something, if that's the case, even if it may benchmark well and look like a good number. If it was a mission critical application, like between holding up a UFC event because you couldn't get your gear on an airplane, like I would not feel comfortable with this.
Cool. Thank you.
All right. Any last questions for Tony? Awesome. Thanks for the presentation. All right. So as I predicted, it looks like we won't have time to talk about the MHC paper, but just as a quick plug, one of the things that people are looking at is if you're trying to improve an LLM, okay, in the paper they say in the background section in section 2 that like you can do what they call micro design. So let's build a better attention, okay? And we've seen lots of research papers, right? There's Linear, there's Mamba, there's all these different things. DeepSeek sparse attention. Then there's people saying we can build better feed forward network layers, better MLPs. And so the most notable thing recently is the shift to mixture of experts. They say there's a macro design thing, which is how do you connect all of these layers together? All right. And that's an area that we have not seen nearly as many research papers as we've seen on the micro design for these two different kinds of layers. And then, of course, prior to LLMs, CNNs, convolutional layers, and things like that. So the key thing is that there's about a year-old research paper from ByteDance where what they did is they made the residual stream, they made the model dimension larger. Okay. The problem with just directly doing this is if you quadruple the size of your residual stream or your model dimension, then for the most part, all of your weights will grow in size by a factor of 16. Okay. So you can't just naively do this. I mean, people do this. That's why, right? Like Claude Opus is bigger than, Claude Haiku, right? But so they wanted to say, can we get some of the benefits of more representational power by having a higher model dimension without paying that cost? So then what you would need to do is, let's say your residual stream's 4 times bigger, you'd have to find a way to squeeze it back down to the original size going into the layer. And then the dimensionality going to a layer is identical, the parameter sizes, the weight matrices are all the same as normal. And then you have to figure out a way how to get back up to 4x coming out of each layer. So that's the hyperconnections paper that was about a year ago. What they found is that if you do this, which they did not try to optimize it, it was much slower, okay, that in fact, for the same number of parameters, you can get a better LLM. You actually get lower loss, you get better performance on benchmarks. The DeepSeek people in this MHC paper, they said, hey, let's try this in our next big DeepSeek model, and it didn't work. The training had issues where basically they had like arithmetic overflows and things like that. So what this technique that ByteDance did in the original hyperconnections paper modified the residual stream But if you guys remember all the way back to CNNs and ResNets, the purpose of the ResNet was to solve the exploding and vanishing gradients problem. And as soon as they inserted these tiny little matrices into the residual stream. So in a 4x residual stream, they had a 4x4 matrix that just does like mixing amongst the different quarters. That was enough to break the fundamental idea of the residual path having no computation, no interference. And then all of a sudden now you can have vanishing and exploding gradients again. So the MHC paper is saying, can we get the benefits without the penalties? Can we constrain this 4x4 matrix into a form that won't allow exploding and vanishing gradients? So if you think about it, you want to constrain somehow the size of the outputs of these layers to be similar to the size of the input of these layers. Okay. And so then how exactly do you do that? Ultimately, what they chose is this thing called doubly stochastic matrices, where the rows and the columns all sum to 1. And what they found is that if you limit these 4x4 matrices to be in that form, then things can't really explode. So they found in practice, they trained, I don't remember what it was. It was 27 billion model or something, but they trained a fairly large model, and the multiplicative effect of all of these 4x4 matrices through all the layers was like a factor of 1.6. So instead of like thousands and exploding things, they got it down to 1.6. So that's obviously not giving you guys tons of detail in this paper, but I think it's a really interesting read. And in particular, just this idea that they're not the only one. There are other papers, but you can look at, people are now looking at not just how do we modify inside the layer, but people are also doing some research now on how do we connect the layers. Is there an opportunity to squeeze a little bit more out? And in my personal opinion, the MHC paper was pretty successful. I do think we're going to see that being adopted in the next generation of models. So I know there's already another DeepSeek model where they just automatically used MHC, even though the model was about something completely different. And so the big test will be when you see the next Quen model, if it has this 4x residual stream MHC business, then that's pretty much the harbinger that everybody's going to be adopting. All right, so that's going to wrap up for today. Thank you for our speakers. Thank you for the great attendance today. The first Saturday each month is when we try to do these talks. So I have not been doing a good job, but I will say right now, I'm soliciting for speakers for, what month is this? February. For the beginning of March, for the beginning of April. A few people filled out the form very nicely over the holidays, and I have not responded. I still have it. I will respond. I haven't responded yet. Next week's event is going to be our final talk for the hands-on machine learning book. So we're in part 2. We talked about deep learning. We got a little bit into CNNs. Ryan talked about NLP. And so we talked about like RNNs, LSTMs, and attention. And so we're going to round things off with, I think the cornucopia for this chapter is autoencoders, GANs, and diffusion models. So quite a bit thrown in there. And there is a new PyTorch version of the book that I haven't looked at yet, but I'll try to add a little bit of color because there have been quite a few advancements in these areas since the third edition book that we're reading came out, especially with the diffusion models. So covering all of that, we won't be going super deep, but for those who are not familiar, we'll do a good review, hopefully give people a good intuition on these other architectures. And I think that wraps things up for today. So thanks, everyone.